Right, it's been a while since you've done any applied physiology, so we're going to do a bit of a revision session, a bit of a recap session in this one. But rather than looking at something discretely, we are going to look at the energy systems, which we did just before we finished. But we're going to dovetail that with muscle fibre types. It's just a nice way to look at some crossover, some application, and also then to understand how one supports the other. I am going to look at all three energy systems, so ATP PC system, lactic acid system and the Krebs cycle, but I'm only going to focus on two muscle fibre types. So I'm going to look at type 1 and type 2X, the two extremes. I'm not really going to talk about type 2A. I'm going to allow you, with the knowledge that we're going to kind of recap over type 1 and type 2X, to be able to make assumptions based on that, bearing in mind that the type 2A has those strength and power qualities as well as the endurance properties of the type 1. Okay, so first and foremost, let's just focus in on motor units. So where we started our muscle fibres, we looked at motor units, a bit of work, bit of recap on summation. And if you remember, motor size or motor unit size is quite important. And if we want to vary force, then as we apply force and that force is not strong enough to complete the task that we're looking to complete, then we then begin to recruit more and larger motor units. So if you remember from your order of recruitment, slow twitch motor units tend to be recruited first. Then if the force is greater, the force required is greater, then type 2X motor units tend then to be recruited. But it's important to recognise and to remember that the type 2X motor units tend to be the bigger motor units because they're very powerful. They require powerful, fast contractions. Something we've got to look at in relation to the energy systems in a second. And the slow twitch motor units tend to be smaller. Okay, so if we remember that point. So we're going to focus first and foremost on the type 2X and the qualities within those type 2X, and then how the energy systems that are able to support that. So the first thing we're going to look at is that a type 2X motor unit has, or a type 2X muscle fibre has a high transmission of action potentials. Okay, so what do we mean by action potentials? Well, action potentials then are those electrical impulses that are sent via the motor neuron pool down the spinal cord, down the central nervous system, and to the muscles that have been chosen to work. And as if we remember, if the summation of those action potentials is strong enough that it reaches the firing threshold, then the motor unit is fired. And according to all or nothing law, it's fired maximally. Remember, within a motor unit, we can't just choose to fire maybe half of the muscle fibres within that motor unit. If the action potentials summate, if they add up to the firing threshold, then due to all or nothing law, the whole motor unit then is fired. And you imagine now a motor unit which is densely packed with muscle fibres, being it's such a large motor unit, is going to produce then a very powerful contraction. So we need to consider then how the energy systems support that. Well, first and foremost, to support that is we've got high levels of phosphocreatine, okay, enabling the ATP-PC system to be really instrumental in the way in which these motor units fire initially. So remember, it's that immediate source of energy. Okay, there's no waste product. That split of the phosphate from the creatine then goes on to resynthesize ATP. And it goes on to resynthesize ATP immediately. It's very, very fast releasing energy. Now remember, that's just for 10 seconds. So in addition to that, another quality of a fast twitch muscle fibre is that it's also got high glycogen stores. Those glycogen stores are then ready for anaerobic glycolysis, so that breakdown of glucose into pyruvate. Okay, so if you remember that from before, so we had our glucose molecules. Remember, we split them from a 6-carbon molecule into a 3-carbon molecule, but ultimately it turns, or we want to convert it into pyruvate. I forgot me spelling there for a second. All right. Now, in order for this to happen, So we've got high levels of phosphocreatine, that immediate store of energy, and we've also got high levels of glycogen stored within the muscle as well. So what else needs to be there? Well, in order for this to work, what we need to have is high myosin ATPase activity. Okay, what does that mean? Well, obviously the enzyme is there to break down. Okay, that's what the job of the enzyme is. So the enzyme myosin ATPase splits ATP, and if there's a high level of activity, it is splitting ATP really quickly. So this is what helps that fast and powerful contraction, that immediate response, that maximal response. Remember, you've got an awful lot of muscle fibers within that motor unit that requires recruiting, okay, an awful lot of muscle fibers within that, and so therefore the firing threshold is going to be high. Remember, they're coming down really quickly as well, so that energy is required very, very quickly and repeated. So our PC stores are absolutely critical to that. In order for them to begin their process, obviously we need to split ATP, and ATP is then split very quickly by the high myosin ATPase activity. What we've also got is a high level glycolytic enzyme activity as well. So after the 8 to 10 seconds which PC stores then supply energy or aid in the resynthesis of ATP to provide energy in these high level, these high intensive muscle fibers, then glycolysis will kick in, because ultimately we run out of phosphocreatine. So within that then, in order to provide a rapid rate of energy production from anaerobic glycolysis, we also need high glycolytic enzyme activity. Now, remember, there is a lack of oxygen here, okay? So as a result, the energy that we are producing, or the energy that we are providing for the fast twitch motor unit, is essentially anaerobic now. So we've moved into the lactic acid system. So what does the lactic acid system do within this process? So if you remember, in the process here for anaerobic glycolysis, that's a real simplified process of anaerobic glycolysis. If you remember here, we have oxidation. Okay, so we have oxidation, which is the stripping of electrons. So remember, oxidation isn't really anything to do with oxygen. Oxidation can take place without oxygen. Oxidation is the stripping of electrons, okay, the removal of electrons from something. So we have our carrier, NAD+, and when we strip that electron, if you remember, it becomes NADH. Now, with the absence of oxygen, NADH now is far too big to enter into the Krebs cycle. Okay, far too big to enter into the mitochondria. And so with that, if this was to stay the case, then unfortunately we'd run out of carriers, we'd run out of that NAD. So in order to maintain that ability to continue anaerobic glycolysis, we have got to offload. This has got to be oxidized as well. So NADH passes those electrons back to pyruvate, and that converts into lactic acid. Okay, if you can just see that. Okay, converts into lactic acid. That lactic acid now is, or the idea of lactic acid is now removed to aerobically respiring tissues to break down. Okay, to break that down and to remove it. Now, that's how the lactic acid system now aids anaerobic glycolysis and aids our ability to continue working maximally for a certain amount of time. But we know it's not a long time, but a certain amount of time. And there's a couple of reasons why it's not a long time. First and foremost, you have to remember that here, all our energy is being produced anaerobically. And if you remember from anaerobic glycolysis, we essentially end up with a net 2 ATP. I realise I'm just filling this now, but when we move on to the next slide, I'll slow down. So we end up with a net 2 ATP. So you have to think now, for all the glycogen we have stored within that muscle, the high levels of glycogen we have stored, thank God we do, because essentially we're burning through it really, really quickly, which is a really inefficient way to create energy. If you remember, through aerobic respiration, through the Krebs cycle, we're going to look at in a second, 34 to 36 ATP are being produced. Here, a net 2 ATP. So ultimately, it needs to be whipped through quickly, hence the high activity of glycolytic enzymes. But fundamentally, glycogen stores are being depleted very quickly. So part of the reason why we become fatigued anaerobically is that we deplete our glycogen levels. But also we have to remember that after a while, at maximum level, we are producing more lactic acid than we're able to remove. And at that instance, we notice here that the H+ ions, okay, the hydrogen ions, create more acid or a greater acidity within the muscle cell. And that's that burning sensation that we feel. Okay, so as a result, we've gone through this. This is how we support that maximal activity in that fast twitch muscle fibre. Ultimately, we provide action potentials really quickly at a regular rate so we can fire maximally. But also, it's the high PC stores and the high level of glycogen stores that keeps that ticking over. Fundamentally, however, we run out of stores very quickly because we aren't getting much for our money. Okay, it's quite an inefficient way, but also that build-up of lactic acid and the build-up of hydrogen ions makes that cell more acidic, and as a result, we struggle. So that's our type 2X. Type 1. Well, if we start the other way, we have quite an efficient model. Now, it does not have high transmission of action potentials. It doesn't have high PC stores and high glycogen level stores, simply because it can't accept high transmission of action potential. So there's actually no need for it. It would be an inefficient use of storage if you have high levels of glycogen stores and PC stores within those slow twitch muscle fibers, not that they can anyway. Okay, but what they do have then are qualities that enable them to work for long periods of time. So first and foremost, we have a high capillary density. That means we are delivering a lot of oxygen, far more oxygen to slow twitch muscle fibers and slow twitch motor units than we are to fast twitch motor units. So we are able to deliver a lot of oxygenated blood. Also, we have a high levels of myoglobin stores, remembering that myoglobin is that storage and supply of oxygen. So far greater in the type 1 muscle fibre rather than the fast twitch muscle fibre. And these two here then combine to deliver far more oxygen to a type 1 muscle fibre. Therefore, they are more geared towards that endurance base. And how does that help? That final kind of put is the fact is that we have a high level, of mitochondrial density. Okay, we have a high number of mitochondria. And by having a high number of mitochondria, it helps in production of energy through the Krebs cycle. Now, obviously, because we're not accepting high transmission of action potentials, as a result, we cannot work anaerobically effectively. Okay, slow twitch muscle fibers can't do that. So how does it maintain endurance performance? Well, it delivers a lot of oxygen. First and foremost, delivers an awful lot of oxygen. As a result, because of that oxygen present, we are able now to commit to the Krebs cycle. Now, Krebs cycle occurs within the mitochondria. And as well as glucose now being effectively and efficiently broken down to provide 34 and 36 ATP, we can also involve triglycerides broken down to fatty acids through beta oxidation, which also enters into the Krebs cycle. So remember, fat molecules contain pretty much double the amount of energy that carbohydrates do. So within the mitochondria, what we have now, because oxygen is present, is that we can have a combination where we combine pyruvate with coenzyme A to create acetyl-CoA. Now can enter into the Krebs cycle. Because oxygen is present, the carriers can release the electrons into the electron transport chain, and hydrogen then can combine with oxygen to produce water and go through the process of hydrolysis. If you remember hydrolysis, if we had I beg your pardon, here's our ATP, and hydrolysis is the breaking of those high energy bonds to create ADP. And obviously those electrons within the electron transport chain are also combined with oxygen then to resynthesize ATP. So as a result, this far more efficient process allows the type 1 muscle fibre to continue to work for long periods of time rather than become easily fatigued.